So first of all, we have to talk about frames of reference and how different observers might see each other. So let's begin by talking about frames of reference. I'm going to use airplanes for an example here. So I'm just going to draw a rudimentary airplane here. There's the wing, there's the fuselage, that's all I will draw of it. And let's say that this airplane is traveling in that direction. And our frame of reference is such that this is forward, this is backward, this is left, and that is right. And if we have another plane following along with him, he's going to have the same frame of reference, assuming he has the same speed and direction. So he's traveling in the same direction, that's the most important thing. And he's going to have forward here, left, right, and backwards. Pretty much the same frame of reference. But what if they're not flying in the same direction? Let's take our second airplane and have him flying that direction. So his forward, his right, left, and backwards are rotated 90 degrees to the frame of reference of the other airplane. So here's airplane number 2, here's airplane number 1, and by flying in a different direction, he is rotating his frame of reference. This will become important when we see what happens when we add that fourth dimension of time. So flying in a different direction rotates your frame of reference. When we get to the nitty-gritty, it's going to be any motion at all rotates your frame of reference, but we'll see that as it comes along. So now for our thought experiment, we're going to put two airplanes between two layers of cloud. There's airplane number 2, here's airplane number 1. They're identical airplanes and they're flying at an identical speed. We'll make that 100 kilometers per hour. Now once again, they're between two layers of cloud. So that means that all the light has been diffused down. They cannot tell where the sun is. They have no visual reference up above. Down below, all the light is being reflected up at them equally from all directions, so they have no visual cues as to where anything is below. The two layers of clouds meet in the horizon and you can't see where they meet. So there's no visual cue as to what's up, down, left, right, or anything. So now we have these two planes flying along at 100 kilometers per hour. And what do they see? So let's look at airplane number 1 first. Now they can't see any visual cues. They can't feel anything. And let's even cover up the instruments to make this as blind as possible. They cannot tell they're moving. Now let's assume that it's perfectly clear day, no wind shear, no turbulence, so they're not feeling any movement at all. So they will feel like they're stationary. If you've ever flown in a commercial airplane, you know you feel like you're stationary, unless you look out the windows and see things moving. Now the observer in airplane number 1 looks over at airplane number 2, and what does he see? Airplane 2 is at exactly the same point, at the 3 o'clock position, not changing. So it looks like airplane number 2 is also not moving. So even though both of them are moving at 100 kilometers per hour, we'll just assume this is to the north, just for convenience. The observers feel like they are not moving and that the other airplane is also not moving. Now, let's say that airplane number 1 makes a 45-degree turn to the left. So now he's traveling in a different direction. So what has happened? His frame of reference has changed. Forward, back, right, left. Compared to his forward, back, right, and left, they're angled 45 degrees to each other. But I'm going to get this clutter out of here for the moment. So what's going to happen? He's still traveling at 100 kilometers per hour. So these planes only travel at 100 kilometers per hour, never faster, never slower. And he made that turn instantly. So he's going 100 kilometers per hour. Should be a little M there too. And he's going 100 kilometers per hour, but they're going at 45-degree angle to each other. What is the observer in airplane number 2 going to see? When he looks out over his left shoulder, he's going to see airplane number 1 falling behind, because he's converted some of his velocity going north to velocity going west. And so by gaining velocity in one direction, he must lose velocity in the other. We're talking about simple vector analysis here. So if you want to see what I'm talking about here, airplane number 2 has a vector going that way. Airplane number 1 has a vector going this way also, and another vector going that way. And do a proper vector analysis. We have one vector and another vector. There's his speed going north, there's his speed going west, and his result is 100 kilometers per hour to the west. What are these two speeds? Well, he's going at a 45-degree angle at the same speed, therefore we've got that 45-90 triangle again. That means that his speed going to the west is going to be 70.7 kilometers per hour, and the speed going north is going to be 70.7 kilometers per hour. So he traded some of his north-going speed to some west-going speed. And of course his speed along his course is still 100 kilometers per hour, and so we've got that 45-90 triangle, and notice that each of these two legs, the opposite and the adjacent, are 0.707 times the length of the hypotenuse. Simple vector analysis there. Okay, so let's reiterate what's going on here. Airplane number 1 has turned to the left at a 45-degree angle to the course of airplane number 2. By doing so, he trades some of his velocity going north for velocity going west, and therefore he loses ground to the other airplane. Now, what is the observer in airplane 1 going to see? Well, I'm not going to rotate this around because I don't want to get any more confusing than I have to. But to him, forward, backward, left, right, his frame of reference is now going this way. And he's going exactly the same speed. And he looks over to the right, and what's he going to see? He's going to see airplane number 2 falling behind. And of course, he's going to see it going further away. So what he's going to see is exactly the same thing. He's going to see that airplane number 2 has traded speed in this direction for speed in that direction. And we're going to find he's got the same 45-90 triangle with 100 kilometers per hour as in the direction he's going, and each of these 70.7. 70.7 kilometers per hour that way, 70.7 kilometers per hour that way. So he sees airplane number 2 doing exactly what airplane number 2 sees him doing. He sees airplane number 2, put it right about there. He has to look over his right shoulder and back. Notice that he's fallen behind. And he's fallen behind by the same amount. So neither plane can tell which is which. In fact, if he somehow didn't know he turned, he wouldn't know if he turned or he turned. He just knows they're going in different directions. And now each observer sees the other one falling back in the direction that they are going. So we see that if we have a two-dimensional space and we have objects that are traveling at always the same constant speed, if one travels at a different direction than the other, it is going to trade velocity in the direction of the first plane for velocity in the direction that it's going, and will lose ground to the other plane. Let's take a look at something else that's happening here. Let's look at the length of the fuselage. Let's say these are interesting airplanes. They're specially designed for this experiment. And let's say the wingspan is 100 meters and the fuselage length is 100 meters. Totally unrealistic, but it'll give us some nice numbers to work with. Well, how far is airplane 1 extending in the direction that airplane 2 is flying? In other words, what is the length of airplane number 1 in the frame of reference of airplane number 2? Well, we will find that the length of that fuselage, which has turned 45 degrees, are you starting to follow me here? 0.707 times its original length. So if it was 100 meters long, now it's only 70.7 meters long. In the direction that airplane number 2 is going, the length of airplane number 1 has contracted to 70.7% of its length when it's traveling in the same direction, or when it appears to be at rest. Now, I know you're thinking, well, come on, it hasn't really changed its length, it's just changed its perspective. Well, if we add time as a fourth dimension, we find that this is more real than if we're doing this in three-dimensional space. So in the direction that airplane number 2 is flying, airplane number 1 has been shortened to a factor of 70.7% of its original length. And let's look in this direction. Okay, so we have a scale here that's kilometers in this direction, kilometers in that direction. The wing is 100 meters long, but now it's turned 45 degrees. So compared to the frame of reference of airplane number 2, which also has a 100-meter long wing, so that's 100 meters, but the length of the wings in the same frame of reference have been shortened to 70.7 meters. So rotating our frame of reference also shortens us in the frame of reference of the other person. So he hasn't shortened according to his own viewpoint or frame of reference, but from the viewpoint of airplane number 2, he has shortened. And of course, we look back the other way, we see that this is 100 meters. Airplane number 2 has shortened in the frame of reference of airplane number 1. So each observer looks over at the other airplane and sees it foreshortened, and they will really see this. And we know, well, it's just an angle of perspective, but what they will see is a foreshortened airplane. Airplane number 1 looks at airplane number 2, it looks foreshortened because it's turned at a 45-degree angle. Airplane number 2 looks back at airplane number 1, it looks foreshortened because it's turned at a 45-degree angle. And once again, we know that that's not really shortened, it's just a matter of perspective and what the other one sees. But once again, as soon as we add time as a fourth dimension, this becomes more real than it does in a three-dimensional space.